Continuing on here in section 7.6, the graph here that we had in part A, we call that exponential growth because as we move from left to right, it grows, it gets bigger. Okay, so that's going to be exponential growth. It gets bigger as we go from left to right. So as x increases, so does our y. It gets bigger. X increases, so does our y. In B here, the only thing different between A and B is this little negative sign. So we're going to do the same idea here. We're going to plug in our values for x and y. I'm going to use -2, -1, 0, 1, and 2. I'm going to plug those values in for my x. So I'm going to have -0.5 times 3 to the negative second power, -0.5 times 3 to the negative first power, -0.5 times 3 to the 0 power, -0.5 times 3 to the first power, and -0.5 times 3 to the second power. Again, the only thing I did there was substitute in my x values for x. Now I'm going to simplify these and reduce so that I get my y values. Okay, negative exponent, I move to the denominator. 3 squared over -0.5. Here I kept them as the decimal instead of switching them to the fraction like I did over here. Either way, I'm going to get -0.5 divided by 9, which is going to give me -1 over 18, or -0.05 repeating. Again, to get rid of a negative exponent, we move it to the denominator, make our exponent positive. -0.5 divided by 3 to the first power is -1/6, or -0.16 repeating. 3 to the 0 power is still just 1, so times -0.5 gives me -0.5. 3 to the first power is 3, times -0.5 gives me -1.5. And 3 squared is 9, times -0.5 gives me -4.5. So again, the only difference here between my values is these are negative, 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 and negative, instead of positive, 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 positive. And that's because our negative is on our 0.5 and we multiply last there. So when I go to plot these, I go to -2, -1/18. I go to -1, -1/6. I go to 0, -0.5, 1, -1.5, and 2, -4.5. Now, I'm going to connect my dots the best that I can here. And again, we're still not going to cross 0 there. Our y value is never going to be 0 there. Our output is never going to be 0 because we're not multiplying by 0. And that's the only way that we can get 0 there. So if we look at A and B, again, the only difference between them is this negative sign. And that negative just flipped it over our x-axis. So it's like if I would have had my purple line here as wet paint, and I would have folded it over my x-axis here, it would have landed where my yellow is, and that's how I would have gotten my second equation there. So the negative just changed it. We call that a reflection, and we'll get to that a little bit later as well. Example 4 is graphing an exponential model, and this is from page 455. Computer mapping software allows us to zoom in on an area to view it with more detail. The function f of x equals 100 times 0.25 raised to the x power models the percent of the original area the map shows after zooming in x times. We're going to graph this function. So here, the graph that I picked here is just in the first quadrant, because when I'm talking about the percent of the original area, okay, my area, or my f of x, is going to be positive. I'm never going to get a negative area. And the number of times we zoom in is always going to be positive as well. We can't zoom in -6 times, for example. So because I'm just dealing with positive values, I'm just in the first quadrant. My function here is f of x equals 100 times 0.25 raised to the x power. I'm going to make a table of values. The only difference here, though, is that my table is going to be a little bit different. I know before I said we're going to use -2, -1, 0, 1, and 2, but here we can't use negative values. We don't have negative zooms. So I'm going to use, starting at 0, 1, 2, 3. We could do 4. We could keep going. But I'm going to do at least 4 points because we want to have a pretty good picture of where our graph's going to go. So now I substitute my x values into my equation for x. I get 100 times 0.25 raised to the 0 power. 100 times 0.25 raised to the first power. 100 times 0.25 raised to the second power. And 100 times 0.25 raised to the third power. 0.25 to the 0 power is 1 times 100 gives me 100. 0.25 to the first power is 0.25 times 100 gives me 25. Here, when I take 0.25 squared times 100, I get 6.25. And when I take 0.25 to the third power times 100, I get 1.5625. Now, I'm going to have to come up with some kind of a scale. Here's the area. Here are my number of zooms. I can't get to 100 on my graph, so I'm going to go by tens. But since I'm only trying to go from 0 to 3 zooms, I'm not going to change my scale there at all. And again, remember our corner point is always 0, 0. Now, to graph my points here, I go to 0, 100. I go to 1, 25. I go to 2, 6.25. 3, 1.5625. I could have plugged in 4 there as well. I could have plugged in 100 if we wanted to. But we can see right now that our values are getting fairly small fairly quickly. So I'm going to go ahead and connect these the best I can. Again, keep in mind, guys, that your graphs don't have to be perfect. What I'm looking for is that your points are about where they need to be. So make sure I can see your points and that we don't cross the x-axis here. We're never going to have a negative area again. And that we put the arrow here to show that it continues. So if we look here, guys, this graph, as we go from left to right, decreases. It gets smaller. And I didn't put an arrow at my 100 point because, again, we can't have negative zooms. So I start at 100, and I get smaller as I go. Since we get smaller from left to right, we call this exponential decay. So here where it decreases, it's decay. On the last ones, we had growth because it went up. Real quick recap here for section 7.6. Some functions model an initial amount that is repeatedly multiplied by the same positive number. In the rules for these functions, the independent variable is an exponent. And that's all I have for section 7.6.